I recently wrote an article called Nietzsche's Eternalist Return, and I'll put a link to that in the description. This video is going to be the second in a series that I'm doing about that, to kind of dig into it and elaborate on what I talk about. And in a way, this will be the main video because it's taking up the main argument that I make, which is that although modern physics disproves Nietzsche's idea of the eternal return as he understood it, as he conceived it, so that would be that the entire universe recurs in exactly the same fashion an infinite number of times, and therefore you live your life over and over again in exactly the same way an infinite number of times. So I say that modern physics does not allow for this. But at the same time, it provides a different way of understanding the eternal return that vindicates the central idea, that vindicates the core insight, which is that everything is eternal. And this is known as the philosophy of eternalism. And scientifically, it's encapsulated in the theory of relativity. So I'm going to be talking about these things and how this gives us a vision of the universe, a vision of reality in which the future simply does. It's not that the future does not exist. It's not that the past ceases to exist, but everything exists together in one whole. Although we necessarily experience from different parts of it. And so that's what I'm going to be talking about, and how that relates to Nietzsche's idea, and how it is, in a sense, actually a purified version of Nietzsche's idea. Just before we jump in, I'll recapitulate the argument from Nietzsche's perspective. This is how Nietzsche saw and put forward the eternal return. This is based on a note that he wrote in his private notebooks in 1888. So this was just 1 year before his final mental breakdown, from which he never recovered. So it's very, very late in his productive life. And I'm just going to go over it briefly here so we know what we're talking about. We know what Nietzsche believed, or seems to have believed, or was at least thought was very, very plausible. And in the first video, I talk about how his comments and his notebooks, there's a certain tension between those and the statements he makes about eternal return publicly, that he makes in his published works, which tend to be either hypothetical or put a kind of literary distance between him and the ideas. So you can see the first video if you want to find out more about that. But my conclusion is that basically Nietzsche did seriously believe in this as a theory of how the universe actually works. Even if he didn't understand it or was not able to demonstrate it scientifically to a sufficient degree to kind of put it forward publicly and stand behind it fully. So here's the note, which is 1066, section 1066 from a work called The Will to Power, which is essentially a collection of his notes. So that's where you can go to if you want to look at the original version, or you can go to the first video as well, where I include it and read it out. The first premise is, if the universe is composed of a definite quantity of force and centers of force, it must pass through a calculable, i.e. finite number of combinations. And so this kind of looks to the first law of thermodynamics, which is that there's no energy is not created or destroyed in the universe, and so there's the same amount of energy at the universe at all times. And centers of force I take him to mean essentially particles. Now, this first premise could have some problems depending on, for instance, whether space is infinitely divisible. If space is infinitely divisible, then there's not a finite number of positions that a particle could occupy. strictly speaking, there's an infinite number of positions that a particle could occupy, and that throws off Nietzsche's kind of proof. And this has been picked up on as well after he put forward the eternal return and kind of disproven in this fashion. If space has like a smallest possible length and is not infinitely divisible, then it fares much better. The second premise is in infinite time, every possible combination must be realized an infinite number of times. So if there's only a finite number of possible combinations and you have infinite time, it's pretty clear to see that eventually, assuming that there's nothing that happens to the system that sort of locks out certain combinations, but things continue to flow and progress, eventually every combination will be repeated. And eventually, since we're dealing with infinite time, it will be repeated an infinite number of times. The third premise, each combination fully determines the next combination. So this is essentially determinism, very hard determinism. If we know the universe in every way at a given time, we can predict with absolute certainty the next moment, what the universe will look like at the next moment, and the next, and the next, and the next. And so this was a popular view, especially among intellectuals at Nietzsche's time, though not a universal view, but certainly a more popular view. And Nietzsche takes this for granted. The fourth premise, the universe is composed of a definite quantity of force and of centers of force. So this is saying simply that this is the case. The universe that we live in has this quality. In the fifth premise, time actually is infinite. And so if we grant all of those premises, the conclusion follows. The universe goes through the exact same series of combinations an infinite number of times. And so if you can imagine just a series of combinations evolving out of each other, and eventually, because this is bound to happen eventually, one repeats. Because of premise 3, because of determinism, the whole series that came after that combination the first time must come after that combination the second time, including eventually itself. So that combination will lead to the third instance of itself, which will lead to all the further series, which will lead to the fourth instance, and this goes on and on forever. And so you get a cycle, you get a chain of events that kind of form a ring, and this is the ring of eternity. This is Nietzsche's eternal return as he understood it. Now I'm going to go to the article and read through it and expand as I go on certain parts of it. So I'm going to start where I left off last time, which is talking about the physicist and mathematician Henri Poincaré, who revealed his recurrence theorem, demonstrating that certain closed systems confined to a finite space will inevitably return to a state arbitrarily close to their initial state. So this was his theorem that he put forward just within a few weeks of Nietzsche's final breakdown, so Nietzsche never got to see it. But basically what it shows is something very, very similar to Nietzsche's idea of the eternal return. Poincaré's not talking specifically about the universe. That's an open question, whether the universe was such a system or not. But certain kinds of systems, he demonstrated, would necessarily repeat themselves, and given an infinite time frame, would repeat themselves an infinite number of times. There's an important qualification there, though, which is that each state would return, so each particle or each part of the system would return to a state arbitrarily close to the initial state. And that phrase, arbitrarily close, is key because it doesn't mean absolutely identical in every respect. What it means in terms of a system in space is that if space is infinitely divisible, you essentially take an area of space. It can be as small as you like. There's no limit to how small it can be. But you take a certain area and you start with the particle in that area, and then you can predict that given an infinite time frame, eventually that particle will return to that area. Now the system needs to be a closed system confined to a finite space. So the space of possibilities, can't be expanding or changing. It has to be the same. It has to be constant. Now, if the universe was such a system, it seems like it would eternally recur. As I mentioned in my previous video, there's perhaps issues with how much that actually does support Nietzsche's eternal return, because the recurrence is arbitrarily close, not absolutely identical. And so, for instance, if a future version or iteration of me sitting here recording this video contains a particle that's offset by a nanometer from where it is now, or let's say 1,000th of a nanometer, does that mean anything? Does that have any effect in the world at all? And if it doesn't, then it seems like this would demonstrate Nietzsche's idea of the eternal return as he conceived it. If the universe were such a system that Poincare recurrence applies to, and if differences below a certain level don't matter, they have no effects, then Poincare essentially would have demonstrated Nietzsche's eternal return. If they do have an effect, that throws the whole thing off, because then the whole system will evolve differently, because Nietzsche's assuming that hard determinism where a given state of the universe absolutely predicts in every way the next state. And so that tiny offset of a particle of my physical body would change me, would change the universe, and so you wouldn't get an absolutely identical recurrence. And so that could be a problem. Now, we can put that to the side for now, because there's bigger problems to come. And so we can focus just on the question of whether the universe is such a system that Poincare recurrence could apply to. So that is to say, whether it is a particular closed system confined to a finite space or not. And the big problem with that is going to be, well, let me read. Given Nietzsche's antagonism to Christianity, it's fitting that a Catholic priest would render his theory unsound. So in this respect, at least, Nietzsche was defeated by a priest. In 1927, just under 4 decades since his collapse and 3 since his death, Father Georges Lemaitre argued the universe was expanding. And in 1931, he proposed the entire universe expanded from a single primeval atom. So I'll just bring his photo onto the screen so you can see him. There he is, Father Lemaitre. And his theory of this expanding universe from a primeval atom became known, of course, as the Big Bang theory, after that initial primordial explosion. And there's a lot of evidence for it nowadays, a lot of evidence, and it's essentially the scientific consensus. Like any scientific theory, though, of course, we can't say it's absolutely certain with 100% accuracy, but it makes sense of the data that we have in a way that's convincing to most scientists today. So we can say that much. Now, there's 3 ways the Big Bang undermines eternal return as conceived by Nietzsche. So first of all, it means that time is not beginningless. It began at the Big Bang, and so there can't have been an infinite number of past cycles. And so on that note, it's not that time was sort of elapsing infinitely before the Big Bang, like there was just empty time where nothing was happening. There was just sort of this static singularity waiting to be. It's that time doesn't make sense in that singularity. Time begins with the Big Bang. It begins with the universe's beginning in this theory. And so it immediately eliminates half of eternity, you could say, for Nietzsche. Because for Nietzsche, time is infinite in both directions. There's an infinitely long past and there's an infinitely long future. And so, with one fell swoop, Big Bang theory eliminates the infinite past. Secondly, it means that space is expanding. There are ever new regions for matter and energy to move into, undermining the recurrence of past states. This is not the kind of system Poincare recurrence could apply to. So this is the key point in regard to Poincare recurrence, because you no longer have this system with a fixed number of possibilities, with a a confined, bounded possibility space, but you have that space growing and growing and expanding and expanding. And so there's always more possible regions for energy and matter to move into. And so there's no necessity that they eventually return to their original positions or arbitrarily close to their original positions, because they can simply move into this new space that's been opened up and create different combinations in that space, and eventually there'll be even more space for them to have even more combinations in, and so on and so forth. And space itself is expanding in this theory, not just that the universe itself is sort of moving into this infinite container of empty space, but space itself is expanding. So there's literally more space in the universe as the universe expands. And so this really in itself just defeats Nietzsche's idea and defeats Nietzsche's reasoning. And then finally, it implies an utterly unproductive final state of the universe. As per the second law of thermodynamics, entropy increases over time. The energy in a system becomes less organized, more dispersed, less usable. Things fall apart, in other words. Unless there's enough gravity in the universe to reverse its expansion, and current evidence does not support this, then it will end in heat death, with all energy evenly spread out. So that's, again, the current predominating theory is that the universe will end in heat death based on the amount of gravity in the universe, the rate of its expansion, which doesn't look like it's going to return to a big crunch. It's not going to kind of compress into another singularity. It's just going to keep going, and eventually all energy is going to be spread out. It's going to be unusable. It's just going to be so thin that you can't do anything with it. You can't kind of assemble people or creatures out of it. And so the universe is kind of just going to exist eternally in this completely unproductive state. That's the idea. Now, Nietzsche knew the second law of thermodynamics. It was around at the time, but he didn't consider it a threat. From his reasoning, if time is beginningless, so if it's infinite in both directions, if heat death were possible, it would have already happened, obviously. But because it hasn't happened, it can't happen, or it can't happen permanently. Maybe it kind of happened for a time and then another universe spontaneously emerged. That's fine. That's consistent with Nietzsche's idea. But absolute heat death can't exist if time is beginningless, because in all that time, it should have happened. Now, the problem is that if you, like we've already seen, we know that time is not beginningless. If the Big Bang Theory is true, the universe is only about 13.8 billion years old. That's the current estimate. And so there's still plenty of time for heat death to manifest. And so once you have heat death, you remove the possibility of new combinations being the same as other old complex combinations, like, for instance, me sitting here recording this video. That won't spontaneously manifest from the thinly spread energy that exists at the heat death of the universe. So all further possibility for kind of complex, intelligent life is cut off at the end of the universe. And so this is how Lemaitre and the Big Bang Theory defeat Nietzsche's idea. It does not work in terms of the Big Bang Theory, though plausible for the physics of his time. Now, there was an even more fundamental revolution in physics. I'll just remove Lemaitre from the screen. In 1905, so this was just 5 years after Nietzsche's death, which occurred a long time after his breakdown, Albert Einstein published his special theory of relativity. Prior to this, physicists had been stumped by a curious paradox. The same speed of light was measured by all observers, regardless of their own velocity. How could this be? And I won't pull a picture of Einstein onto the screen. I don't think that's necessary because he's kind of the most iconic kind of face, I suppose, in modern Western culture, or one of the most iconic faces in modern Western culture. But so here's where we get to the physics, and I've got a couple of videos, or a few videos actually lined up that we can watch to kind of understand this. And it was really fascinating for me going through this study and getting my mind around relativity theory and what that actually means conceptually, like being able to understand it conceptually, not just in terms of mathematical equations. And so this paradox about the speed of light, the same speed of light was measured by all observers regardless of their own velocity. This was what was really puzzling physicists coming into the start of the 20th century. And we can understand this in this way. If you're driving a car at 100 kilometers an hour, then a car coming toward you at 80 kilometers an hour will seem to be racing toward you at 180 kilometers an hour. You add those speeds together. Because if you kind of imagine that you're stationary, say, then the speed of that oncoming car will be your, like, let's say, actual speed plus its speed. It'll be a lot faster than what it would look like if someone's standing on the side of the road. And if you're both going the same direction, so you and the other car are going the same direction, then because you're going faster than it, it's receding, it's moving backwards at 20 kilometers an hour from your perspective. And so this is essential because we're talking about from particular observers' perspectives. So we knew that light was an electromagnetic wave, and it should make a difference if we're moving into or away from the wave when we measure it. So that's the key thing here. Now, don't get that confused with sort of the speed of light as dependent on what emits it. So previously it was understood that light was sort of only particles before we understood it as being a wave. And so if your car is going 100 kilometers an hour and you shine a beam of light forward, then it will be the speed of light plus 100 kilometers an hour under that understanding. But this doesn't work when we're talking about light as waves. Light as waves will always propagate at the same speed. So we're not talking about that issue. So what we're talking about is the perspective of the observer. If you're moving into a wave, it will seem faster. If you're moving with the wave, it will seem slower, or it may actually seem stationary if you're moving it as fast as it is. And so this was the problem. Now, there's a related problem, which is that just like waves in water and sound waves in air, it was assumed that light waves must travel through a medium. There must be something that the wave propagates through. And this was hypothesized to be what they called the luminiferous ether. And so the whole universe was filled with this ether, this kind of extremely fine substance, which allowed things to move through it without any perceptible resistance, but also had to be rigid enough for the extremely fast propagation of light to happen. So it was a bit of a paradoxical thing that was supposed to be supporting light. Now, because of the ether, and because the Earth was moving through the ether, you would expect to feel or experience or measure what you could call the ether wind. This is what they called it at the time. The ether wind, just like if you're racing in a car at 100 kilometers an hour with the windows down, you'll feel a wind against your face, even if it's perfectly still outside. There's no actual wind, but you experience the wind because you're racing into the air. So likewise, if the Earth is racing through the ether, there should be a detectable ether wind. And the wind will, if you will, impede light going into it and aid light going with it. And so, thought about this way, we can understand the decisive experiment in this regard, which was by Albert Michelson and Edward Morley in 1887. So this was the experiment that established that light goes the same speed in every orientation. And so think about how fast the Earth is moving through space. So it's going around the sun, hurtling around the sun at 100,000 kilometers an hour. It's also rotating at an incredibly fast speed around its own axis. We'd expect to detect a relative difference in the speed of light, given that this was the case. If we're going into the ether wind, or if the light is going into the ether wind, we should experience it going slower than if it's going with the ether wind. If light is going perpendicular to the ether, again, it will be a different measured speed. And this is the experiment that they conducted. I'll just bring a diagram down of the experiment. So this is called a Michelson interferometer. Light comes from the laser on the left, hits a half-transparent mirror in the middle, and then the beam splits into two directions. One goes up to the top and the other continues to the right. They're reflected from their respective mirrors back into the middle, where they're split again, and what you get in the screen at the bottom is a beam of light that's traveled to the right mirror and a beam of light that's traveled to the top mirror. And they combine and they form an interference pattern. Now, you'll get a different interference pattern if the speed of light on one side is different to the other. And so that's how they were trying to detect a difference. And so if, let's say, one of those planes, let's say that the horizontal plane is aligned with the ether wind, and then the vertical one is perpendicular to the ether wind. So if that's the case, then the speed of light from the light going between the laser and the mirror on the right, the speed of that light is ultimately going to be slower than the light traveling up to the top and back down again. And the reason for that is that it's going to be impeded by the ether wind more than it's going to be aided by it on its return journey. It's going to spend more time fighting the ether wind, and so overall then it's going to be slower. And so when it recombines with the light in the middle and goes down to the screen at the bottom, it's going to be aligned in a slightly different way. That's going to produce a slightly different interference pattern. That's what you would expect to see, but that's not what Michelson and Morley saw. So what Michelson and Morley saw was that whichever way you oriented your apparatus, and regardless of when you did the experiment, so regardless of where the Earth was positioned in relation to the ether wind, it didn't make a difference. The same speed of light was measured every time, basically. And now we know that that speed of light, the absolute speed of light, is 299,792,458 meters per second. At the time, I don't think that was the exact figure that was measured, but that's now the official speed of light. And so this was an amazing result. Michelson and Morley went into the experiment thinking that they were going to demonstrate the ether wind, and they came out effectively having demonstrated that there cannot be an ether wind, and this idea of the luminiferous ether doesn't make much sense. The problem is, what do you replace it with? What does make sense? And this is where Einstein comes in with his special theory of relativity. And so he does something extraordinary to make sense of this. We know that the speed of light is absolute, but how could that be? Well, maybe time and space are relative. So it took me a while to fully understand conceptually what is going on with the special theory of relativity. But I hope that if you're not already familiar with it enough to sort of grasp it, to understand it, that maybe this video will help somewhat. So this is the classic thought experiment to start off with. I believe Einstein uses it himself. Imagine you're standing beside a railroad in which a train is traveling close to the speed of light. You see two simultaneous flashes of light, one right in front of the train and one right behind it. What would you see if you were standing in the middle of the train? Because you'd be racing toward the front flash and away from the other, the light of the front flash would reach you first. And because you would measure the same speed of light from both directions, you would conclude the two flashes were not simultaneous. To the passenger on the train, the person standing by the tracks is actually racing backward, toward the rear and away from the front flash, which is why they see the two flashes at the same time. Whether two events are simultaneous or not is a matter of perspective, and in relativity there is no privileged perspective. So I've got a video lined up, a couple of videos actually, which may help to elucidate this. So here is the first one.
Imagine two observers, one seated in the center of a speeding train car, and another standing on the platform as the train races by. As the center of the car passes the observer on the platform, he sees two bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time, so he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to his eyes at the same speed, the speed of light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear. But what does the passenger see? As her friend on the platform predicted, the passenger does notice the flash from the front before the flash from the rear, but her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct? The observer on the platform, who claims that the strikes happened.
So the key thing here is that the speed of light is constant in both frames of reference. And so neither observer can say, oh, I'm just moving in relation to that speed to the light, and so for that reason, that's why I experience one before the other, or that's why I experience them simultaneously. But they both have to say that since the speed of light is the same, and the light's originating the same distance away from me, then if I experience one first before the other, it really happened first. or if they experience it at the same time, it really happened at the same time. And so that's the key thing, that the speed of light being constant means that each observer, no matter how fast they're moving or where they're moving or in what direction, if they see a different order of events for them, it really happened that way. It's not just a matter of perception. There's no way that they could calculate to find out sort of when it really happened, so to speak. That is their plane of simultaneity. That is their present, their now. And it may be different from a different observer's present. Now, there's another video that looks at it a bit of a different way. Instead of imagining two flashes of light on each end of a vehicle, you imagine light coming from the middle of a vehicle. So I'll show you that now.
In special relativity, one fundamental idea is that two events can occur simultaneously for one person, but at different moments for someone else. To understand, let's imagine the following scenario. The passenger in the spaceship holds two torchlights, one which he points backwards and the other one forwards. His role will be to light the two torchlights exactly at the same time. He will then look at which moment the two light rays reach the edge of the spaceship. He begins by lighting the two torchlights at the same time. Since from his point of view, the spaceship stays motionless, the light rays will propagate both sides in the same way. Thus, they will reach the two ends of the spaceship at the same moment. For the passenger, the two events are simultaneous. Both light rays reach the two edges of the spaceship at the same moment. But let's now look at this same situation as it is perceived by an observer on the surface of the planet. We previously saw that the speed of light was a constant. Therefore, when the two torchlights are turned on, light will spread with the same speed on both sides. But at the same time, the spaceship is moving forwards. As such, the light ray sent towards the left will reach the back of the spaceship before the light ray on the right reaches the front. From this point of view, the two events are not simultaneous. The light rays do not reach the two sides of the spaceship at the same time. To explain this paradox, we must put to the side our intuitive understanding of time.
So hopefully those videos were helpful to kind of understand what's going on here. Now this is known as the relativity of simultaneity. What is simultaneous from one perspective is not necessarily simultaneous from other perspectives. It's relative to the velocity of the observer. And it leads to two other extraordinary phenomena: length contraction and time dilation. So we'll look first at length contraction. I'll play a video and then I will try and explain it as best I can.
To give you some practical example, imagine you have a ship and you are at rest relative to this ship, and you measure its length to be 5 meters. Now imagine an observer moving relative to this ship, and he wants to measure the length of the ship, so he measures the positions of front and back end of the ship simultaneously and subtract them. He finds out that the ship is just 4 meters long, but how so? This is however no surprise for the observer that is in the ship's rest frame, since in his frame of reference, the moving observer measured the front end of the ship first and then the back end of the ship later. So if the object is moving relative to you, you have a different simultaneity plane than the observer in the object's rest frame.
So the key point there is that in order to measure something, you have to locate each end of it at the same time. And so if simultaneity is relative, if what events are simultaneous depends on the velocity of the observer, then this is going to differ depending on the speed in which you're traveling. And so that's the basic idea behind length contraction. So if we think about the train that we've used as an example before, and the flashes of light at each end of it, so let's say that each flash occurs at exactly each end, and so we can actually use the flashes to determine how long the train is. Because they're simultaneous from the perspective of the person standing in the middle of the station, because they happen simultaneously, then where they happen determines the length of the train. So where each flash occurs, and we just, so we observe where they occur, and we see what the distance between them is, that's the length of the train to the person standing on the station. But to the passenger on the train, the flashes are not simultaneous. So the outside observer goes about it wrong from the perspective of the person on the train. So from the perspective of the person of the train, the person on the station is racing backwards. And so what happens is first that outside observer measures the position on the front of the train, at the front of the train, and then, after it's moved on, the position at the back of the train. In other words, the person outside the train measures a shorter train. So let me go over that very briefly again. So the person on the station, from the person on the station's perspective, the events are simultaneous. So the measurement that he makes is the true length of the train. But for the person on the train, because the front flash happens first and then the back flash happens, what the person on the train sees the person on the station doing is measuring the front of the train first and then measuring the back. And so if you imagine that between those measurements, the train has moved on, the back is now further forward, if you will, and so the total length of the train is shorter. And so that's how that works in regard to the train. We can also think about it in terms of the spaceship example from a previous video. The two flashlight beams going in opposite directions, to the front of the ship and the back of the ship. So from the perspective of the person on the spaceship, they hit the ends of the ship at the same time. Light propagates in all directions at the same speed. But let's say that you have someone on a planet that they're passing, or a spaceship coming toward them. From the other perspective, the perspective of the people outside the ship, then it's a different story. Because from their perspective, the light hits the back of the ship first, because the ship is going toward, the back of the ship is racing toward the beam of light that's going towards the back of the ship. And so the back of the ship, from their perspective, is measured first, and then the front of the ship is measured after that. And so what that gives us is, of course, it gives us a longer ship. And so from the perspective of the person outside, the person inside the spaceship is measuring the ship wrong. And that's why the person on the inside of the ship measures a longer ship than the person outside. So again, in this example, for the person outside the vehicle is shorter. Its length is contracted. From the perspective of the person outside the vehicle is contracted. And that's length contraction. And then finally, we have time dilation. This is another extraordinary phenomenon associated with the relativity of simultaneity. So I'll play a video regarding that.
Finally, a third direct consequence of the invariance of the speed of light is what we call time dilation. To understand this, let's consider the following experiment. The passenger inside the spaceship will grab a flashlight once again, this time pointing it towards the ceiling. At a given moment, he will turn on the light and observe the time it takes for the light ray to reach the ceiling of the spaceship. Once again, the problem changes if we decide to observe the same situation, but from the planet. For the observer on the planet, the spaceship and the passenger inside are both moving. Thus, the beam of light will have to travel not only the height of the ceiling, but will also have to travel towards the right, following the movement of the spaceship. From this point of view, the light ray must travel a greater distance. Consequently, just as it takes more time to cross a road diagonally rather than by its width, it will take light longer to reach the ceiling of the spaceship. For this observer, watching the situation from the planet, the light ray has thus taken more time to reach the top of the spaceship. In general, this observer will see the insides of the spaceship evolving in slow motion. If the passenger on the ship decided to show him a clock, from the planet we would see this clock tick in slow motion. More generally, when an object moves extremely fast compared to us, we see its rear and front decelerate.
Okay, so that is time dilation, and that example that they showed you is often phrased in terms of a light clock, and so that is basically what you saw with the flashlight beam going upwards, except that in this example of the light clock, a beam of light travels up, it is reflected down again, and it registers at the base as a single tick of a clock. And so this is considered sort of the most basic possible clock. And so that sort of directly links it to time. Now, you know, people, all material things are built of electromagnetic phenomena. And so this applies to everything. You could say everything is made out of light in a certain way. And so this, again, like the video pointed out, from the perspective of someone outside the spaceship, from the perspective of someone who is not traveling at that speed, time inside the spaceship will appear to be evolving at a slower rate. Clocks will tick slower. The physiological processes of the human organism will occur at a slower rate. People will move slower. Objects will fall slower. Everything will occur at a slower rate, which is just mind-bending in a way. But that's how it is. And so, briefly, I'll link that back to the relativity of simultaneity to show how that better links in with that, even though you can also see it from the light clock example, which is effectively what we just saw. So the key to understand it in terms of the relativity of simultaneity is that clocks that are synchronized in one frame of reference are not synchronized in another. So we'll go back to the example of the train. A train is passing the station, at each end of which a clock has been placed. So there's a clock at each end of the station, and if we're standing at the exact midpoint of the station, we can know that the two clocks are synchronized if we emit a flash of light and that they read exactly the same time the moment it reaches them. So we note that when the train passed the first clock and then the second, so we note rather when the train passed the first clock and then when it passed the second, and we find that it took precisely 1.2 seconds, let's say, for the train to pass the station. However, if we're on board the train, we see the station racing backwards and the light emitted from the midpoint hitting the front clock first. So that light emitted from the midpoint where we're checking whether the clocks are synchronized, right? But from the perspective of the person on the train, that light that is emitted from the midpoint hits the front clock first. So this is what we have to remember. And so from the perspective of the person on the train, the two clocks are not in fact synchronized. The event that we perceived, if we're standing on the station, that showed us that the clocks were synchronized, the very same event shows the person on the train that they're not synchronized, and that the front clock is ahead of the other clock. So it's running ahead of the other clock. Let's say that according to a clock on board the train, it takes exactly 1 second for the train to pass the station. From our perspective on the station, time on the train is dilated. From our perspective on the train, the clocks on the station are out of sync. So just to be even more clear, why is it that from the perspective of the person on the station, time on the train is dilated? It's because the two clocks on the station are not in sync from the perspective of the person on the train. And so their readings don't reflect reality. And so when the train passes the first one, the reading that it gives is not an accurate reading because it's not in sync with the other clock. It's ahead of the other clock. And so the overall time it takes for the train to pass the station is actually greater than what the person on the train measures it to be. And so that's how time dilation links into the relativity of simultaneity. So let's go back to the article. And so, yeah, I'll skip over the next couple of sentences, I think, because I've covered it pretty well in just this last little bit that we've done. Observers will disagree about the length. They'll disagree about the flow of time. And then from the passenger's perspective, since the outside world is racing backward, it will be contracted and evolve in slow motion. So from the perspective of the person on the train, the outside world actually has the same effects happening to it. If from your perspective and whatever frame of reference you're at, the other frames of reference will be you could say, distorted frames. They would be the ones that are length contracted and time dilated, which is really interesting. And this is all to do with the fact that in special relativity, there is no privileged frame of reference. There is no way we can say that a particular frame of reference is the frame of reference. All the laws of physics hold in every frame of reference. And so just as light, it has the same speed in every frame of reference. And so all we can talk about is relative differences. We can't say that there's an absolute frame against which we can measure all the other frames. That breaks down in special relativity. Now, together these principles solve the problem that Einstein faced. Speed is distance over time, and because distance and time vary in just the right ways, the speed of light remains constant. In other words, if time dilates and length contracts, light has more time to go a shorter distance. So hopefully you can see the brilliance of that solution. And there's mathematical transformations you can use, the Lorentz transformations, to convert between different frames of reference. But we don't need to think about those here. We can understand it conceptually, hopefully, just based on that principle of, essentially that principle that the speed of light is absolute in every frame. We can derive from that all the other effects in principle. Okay, so now to move from science to philosophy. So we're going to talk about time, and we're going to talk about specifically the theory of eternalism. Einstein's theory of relativity would have delighted this perspectivist Nietzsche, who once remarked, "There is only a perspective seeing, only a perspective knowing. And that quote is from The Genealogy of Morals, a very famous quote. But it would also have given him a new way to understand eternal return. We can distinguish two main views about time: Presentism and Eternalism. So Presentism holds that nothing exists outside the present. The past has ceased to exist, and the future does not yet exist. So this is, you could say, more or less the common sense view of time. That which is in the past no longer exists, or the events at least of the past no longer exist, and the events that are coming in the future do not yet exist. Only the present moment exists. Whatever is in the present moment is what exists. On the other hand, eternalism holds that everything, past, present, and future, equally exists. The universe is one vast block of space and time. Things are located in both space and time. So things have a location in time just as they have a location in space. And this is known as block time or the block universe. And I think that the way I've put it here, everything past, present, and future equally exists, is probably the best way to phrase it. It's called eternalism. And so another way that we could phrase it is that everything exists eternally, and that there's truth to that. There's a sense in which that's true. But it's maybe more precise to say that everything equally exists, regardless of whether it's in the past, present, or future. And I think I'll circle back to that later when I talk about kind of misapprehensions about eternalism. Now, the special theory of relativity strongly implies an eternalist view of time. As the physicist Roger Penrose highlighted with his Andromeda paradox, the relativity of simultaneity means that two people walking toward each other on the street may inhabit very different presents. So they'll have different planes of simultaneity, different planes on which events are aligned as being at the same time. For one of them, an invasion fleet from the distant Andromeda galaxy is on its way to Earth. For the other, the Andromedans haven't even decided to invade yet. But how could this be unless these events just exist in space-time all along? And if we consider all the possible presents, so actually I'll stop there for a second, because I have a slide for this one. So this is from Penrose's book, The Emperor's New Mind. And so this is a diagram that he includes. And so this is basically what I described. This is the paradox. It's in a very abstract form, but there you go. And so you can see that the planes of simultaneity for A and B are different based on their velocities. And even though their velocities are very small, they're slowly walking past each other, that compounds or maximizes based on the extreme distance to the Andromeda galaxy. And so you can see that for B, the Andromedans haven't even decided whether to invade, and they certainly haven't launched their fleet. But for A, the fleet's already on the way. The decision is made, and the fleet has been launched. And yet, these two people are walking toward each other slowly on a street on Earth. And so how could this be? As Penrose puts it in the book, how can there still be some uncertainty as to the outcome of that decision if to either person the decision had already been made or has already been made? Then surely there cannot be any uncertainty. The launching of the space fleet is an inevitability. And so it would seem that all the events are determined, might be one way to put it, or have already happened would be another way to put it. These are kind of clumsy ways to put it, and I think it's just better to say that all the events along that timeline exist. Okay, we might say, but that only shows that one of them was mistaken. What if someone was in the genuine present, the threshold where what does not yet exist comes into existence? So what do we do with that? But again, we have to come back to the fact that in relativity, there's no privileged observers and there's no absolute perspective from which to interpret all the rest. And that in turn creates a big problem. Because if we consider all the possible presence of all possible observers in spacetime, there remains no region of spacetime that wouldn't be present or past to someone. So we can kind of follow that reasoning out, and we can find that actually there's no space, if you will, there's no area of spacetime which this absolute future could possibly occupy. And so I will play another video that really helped me to understand this point.
Let's get back to the question. What does all this say about the reality of the past and future? Well, imagine that the future is created as a wave of the present sweeping out a block universe. But where is that wave? Whose slice? At a given location in space, you can lay down all possible time slices representing possible presents. The largest tilts are for things travelling at the speed of light, and these sweep out the future light cone. In front of the future light cone is a region that is in the future for everyone, no matter what their speed. So is that the future that doesn't exist until created by the evolving present? Well, that can't be right. Consider the time slice of our present. We can imagine other observers on that time slice that surely must exist. After all, they could have travelled to those points from our own past. They have future light cones similar to ours, but offset in space from ours. The space beneath their future light cones defines all possible definitions of the past to them, just like it does for us. So now, fill our present time slice with observers, and there remains no part of the block universe that couldn't be considered the past according to someone who lives in our present. Let's take stock.
Okay, so you can kind of see from that there's no way that we can say, given special relativity, that there's an absolute future, that there's a future that couldn't be someone's present or past. If you consider other possible observers, if you also consider their possible other observers, the whole universe becomes open to being well, not even open to being. It's necessarily the case that the rest of the universe is in the present or past, at least for some potential observer, which is a problem. And so, well, it's a problem if you're a presentist. It's certainly not a problem if you're a eternalist. So let's go back to the article. And so essentially, even just considering special relativity, we've shown that presentism doesn't really work, and that everything must exist, full stop. Everything past, present, or future, from our perspective, must exist. Now, Einstein went on from special relativity, which is what he put forward in 1905, and in 1915, he presented his general theory of relativity. I'll talk about this only very briefly, but he broadened the theory to account for gravity. Gravity was no longer a force, but the shape of space-time itself, which curves around massive objects. Near them, time stretches out, and this is called gravitational time dilation. Clocks move slower the closer they are to the surface of the Earth. We constantly need to correct for this for GPS satellites to work. So here's another slide I prepared. You've probably seen something like this before. I was thinking of maybe showing a video or an animation of it, but you can kind of visualize, you can kind of see what that would probably look like. So massive objects curve space-time, and you can see there that that's happening with the Earth, and then that essentially is what gravity is. And so the moon that orbits the Earth is kind of following that that curvature around. It's kind of continually falling into the Earth, rolling into the Earth, something like that. And so that is Einstein's account of gravity. And the closer that you get to Earth, because it's space-time, it's not just space, time stretches out, you get time dilation, and therefore gravitational time dilation, and therefore time depends on the geometry of space, which in turn depends on the objects in space, the masses and the distribution of objects in space. And so what are the implications of this? Well, in special relativity, space-time is smooth. Though observers have different presents, each only has one, which extends throughout the universe, if you will. But in general relativity, an observer's present depends not only on their velocity, which is the only thing that really matters in terms of special relativity, but also on the distribution in mass of matter, like I've noted. How we define a universal present for a given observer depends on how we choose to slice up space-time, which is ultimately somewhat arbitrary, and time is not only relative, but radically local. Radically local because, again, you get gravitational time dilation, and so that warps space-time around it. And it's localized. It's not something that's sort of universally distributed evenly throughout the universe. It's localized. And so it's even worse. Even though special relativity is sufficient to discredit presentism, at least in my view, and it seems to be that way from the logic of this, even so, general relativity just makes it even more irretrievable, you could say, because there's no kind of universal time slices anyway, even if we can't choose between them. And this seems like a death blow for presentism, like I've said. Now, the block universe, eternalism, seems far from our common sense view, in which time flows. Or at least that's what we say. That's what we say. We say time flows. If everything already exists within the block universe, wouldn't it just be static? So this might be the first kind of obvious rebuttal or objection to eternalism. Things aren't static. Things move, they change, they flow. They don't just kind of stay there statically. And this was an assumption behind perhaps the most famous paper in the philosophy of time. This is Jamie McTaggart's The Unreality of Time, which was published in 1908. That is to say, if we do assume time's reality. The paper is valuable because it shows first how the common sense presentist view is incoherent, and it's also valuable because it illustrates a basic mistake about eternalism. So it's valuable in spite of itself, as I'll point out. For McTaggart, time implies both an A series and a B series. In an A series, events are ordered from future to present to past. And in a B series, events are ordered as earlier or later than each other. Time requires change, and because the relations between events, that is to say the B series, are unchanging, this must come from their relation to the A series. An event is first future, then present, then past. So I'm going to pause there because I have one more slide about this. So here's McTaggart, and here are his A series and B series. In the B series, events are ordered in relation to each other alone. So time 2 is after time 1 but before time 3, let's say. And in the A series, events are ordered in relation to past, present, and future. Now, a couple of qualifications here about how the A series relates to Presentism and how the B series relates to Eternalism as instantiated in the theory of relativity. So the B series is kind of prototypically Eternalist, but the theory of relativity complicates this a bit because, as we've seen, whether one event is before another event depends on the frame of reference, depends on the perspective. And so in one frame of reference it may be before, in another they may be simultaneous, and in a third they may be it may be after. Now, I would say that this is still a kind of a B series, and so it still fits within the spirit of the B series because you can transform between these different perspectives using the Lorentz transformations. So events have an ordered relation to each other. They have a determinate ordered relation to each other in four-dimensional space-time, but what plane of simultaneity a observer occupies, that will change the order of events to that observer. But in themselves, the events have an ordered relationship, and that's why I think that the B series can be used to describe Einstein's relativity. Now, does the A series represent presentism? Well, when I first wrote the article and I first recorded this video, and this part of the video is an insert that I am doing after I recorded the main video, I assumed that that was the case. And generally it is taken to be the case that the A series of McTaggart broadly reflects presentism. But there is a complication because McTaggart assumes that the events sort of actually transition between future, present, and past. He assumes that first they have the quality or the relation future, and then they have the quality or relation present, and then they have the quality or relation past. But to actually have a relation or a quality probably means that they have to exist. And of course, the presentist says that they don't exist in the future and they don't exist in the past. So it might be argued that this doesn't actually capture presentism. I would say that it still does reflect the presentist perspective because the presentist is concerned to divide reality between an objective future, an objective present, and an objective past, and can still meaningfully talk about events occurring in the past and perhaps even events occurring in the future. And so because reality is continually transitioning, is continually changing, and changing in this relationship of past, present, and future, I think that the basic challenge, the basic insight of the A series holds, and so the basic challenge to the A series also holds. How do you get this change or transition? So McTaggart discounts a B series only view, first of all, as being able to explain time. What McTaggart wants to do is he wants to be able to explain time. What's a correct theory of time? And if we just talk about time in terms of determinate relationships between events, he says we don't have time because we don't have change. To get change, we need to introduce the A series. Again, that an event is first in the future, and it then becomes in the present, and then it moves to the past, or something like that. It has these different relationships. The B series has this changing relationship to the A series. So we could say, in other words, change occurs because an event changes its position in the A series. Change is used to explain change, in other words. Right? So if we have, we can say that T1 is before T2, which is before T3, That's fine. But let's say we want to relate T2 to the A series. So we say first it is in the future, then it is in the present, then it is in the past. And so we're trying to do that in order to explain change. We're trying to explain change, which is an ingredient of time. But notice what we're doing when we say that. First it's this, then it's that, then it's that. We're saying it changes. We're saying it is T2 has a relationship to the near future, or is in the near future, or however you want to phrase it. And then it moves into the present, and then it moves into the past. Or it has this quality, and then it has this quality, and then it has this quality. It changes qualities, it changes locations, it changes, however you want to phrase it, it changes. And so we haven't actually explained change, we've presupposed change. And so we haven't explained anything at all. Change is used to explain change, a vicious circle. And if the first level of change requires an A series, the second level must also, and so on, in a vicious infinite regress. So this is McTaggart's argument, not mine. This is McTaggart's argument. And for this reason, he says that this doesn't work. Presentism basically does not work because you have to invoke change to explain change, and that just presupposes like an infinite regress of A series in order to account for. So you get a vicious circle, you get an infinite regress, you don't get any real explanation. Presentism falls apart, and then McTaggart says, therefore time is unreal. So this is the unreality of time, the title of his article, and that's the thing that he's arguing for. And the reason he falls back onto this idea that time is unreal is because he doesn't see the B series as being viable to explain time. This is where I disagree with him. What if all you need is the B series? McTaggart's rejection of eternalism depends on the fallacy that time itself flows, that the A series and the B series move past each other. But time doesn't flow. Time is flow. Change is already inherent in the B series as the ordered sequence of events that make up a changing object. An event is a momentary instance of change. It doesn't change. Eternalist spacetime, the B series updated for relativity, isn't static just because everything exists within it. Right? This should make sense. If we're talking about time in terms of a B series, what we're actually describing is change. Because we're talking about, if we're talking about a temporal series, we're talking about change. We're talking about how things are different over time. And so it's the difference again between saying time flows versus time is flow. I think it's much more accurate to say time is flow. Time itself doesn't flow. When we're talking about time flowing, essentially we're saying that events themselves have to change. And this is precisely what McTaggart is saying in his article. He's saying that an event, a momentary event, first has to be future, then present, then past, then further in the past, then further in the past, then further in the past. It has to continually change. But you see what he's doing there. He's saying an event, which is already an instance of change by its very nature, has to change in order to have change. That's not necessary. That doesn't make sense. You can just keep that first level of change by saying that the event itself is an instance of change. What that looks like over time is a whole bunch of events which forms a B series. That is the B series. Now, note that we haven't exactly explained change or time. We've, I would say, accurately described them, but we haven't explained them. And I think that's important to realize, because I think that it may be at least very difficult, perhaps impossible, to explain things as fundamental as time and change. The metaphor, time flows, I think that this comes from It feels compelling, the idea that time flows, because it pictures one of time's most salient manifestations, the swiftly flowing stream. But this is an image of its effects, if you will, the effects of time, not a description of its nature. This is not to say that we can ultimately explain time. It may be something fundamental. So again, like I said, it may be something fundamental. But you can see how the very image of how we notice time and what's salient about things that remind us of time, right, is their flowing nature, their swiftly changing. And so we attribute that to time itself. We say time itself changes. But it doesn't make sense to say that time itself changes. Time is change, or at least change is implicit in time, is part of time. Part of time, what time is, or what time means. And so we successfully, well, there may be another reason we kind of use that metaphor, time flows. It's almost like we're saying time is time. It's almost like we're recognizing that time is fundamental and can't be explained. And we're sort of just saying, oh, time flows. It's like we're just saying time is time. So at once we're sort of eliciting its most salient effects in the world, and in the other, and in the same breath, we're kind of maybe just asserting it as being fundamental. Time is time. But note that time is subtly different than time is in time, which I think is what actually we get when we say time flows. When we say time flows, what we actually get is time is in time. Time changes. To change, you need time. So you need a second order time, you need a third order time. But what we really want to say is just time is time. Time is what it is, you know what it is, and we can picture it and understand it in terms of a B series or in terms of the space-time of relativity. But it doesn't need sort of these higher order levels of time in order to change. Presentism doesn't make sense. It's all just there. The whole universe in space and time is just there, and that doesn't make it static. So that's the key thing that I wanted to object to, was the idea that an eternalist space-time is static, that it doesn't move, that it doesn't change. It is change. It can change. It contains change within it. It contains movement within it. It is a picture of movement. It is a description of movement. It is how we can represent movement. Now, I think part of the problem is that we're looking at it visually, sort of in our minds from the outside. We're looking at a great big block of the universe, and so we say, okay, that's static. But of course, we're in it. We're in it, and we're moving through it, if you will. And so that's a different perspective. Now, that brings us to a second potential objection, which is, how can eternalism account for the experienced present? Even if there's no absolute present, it certainly seems that I'm living my life from a particular point within it, which continually sweeps forward in time. If my whole life exists in block time, why is there any subjective present at all? In other words, if the block universe is the truth of things, why do I experience time and change at all? Why don't I just experience the whole of my life in the whole of the universe, if you will, all at once? Now, an eternalist would respond that we experience our life from every point within it. Though to a being in time, what this looks like is exactly what we get. So a eternalist would kind of, to a degree, bite that bullet, but to a degree, nuance it a bit. We do experience our life, if we're talking about our individual life, we do experience that from every point in it. We experience, if we live to be an elderly person, we experience it from the perspective of that elderly person. We experience it from the perspective of a baby and a child. We experience it from every perspective in between. We experience it all. But for a being in time, what this looks like is what we get. It doesn't look different than that. One moment flows into the next in the temporal order. When we experience our life, we experience this flow. Just like a being in space, a being in time has to experience from somewhere. And so each of us experiences our whole life, but from the moments within it. So that's the key. So because moments flow into each other in this way, that is to say that they're continuous with each other, they are arranged such that one moment it meaningfully relates to the next and meaningfully relates to the previous. You can insert yourself into any point in your life and you will have the same experience that I'm here now and I was just there then and I will be just there in a moment. Of course, looking forward, you don't know exactly where you'll be, but you have an anticipation perhaps. And so you will have that same experience wherever you are. Just like if I put myself back to where I was 10 minutes ago, if I could just drop myself back into my life, and it had to be exactly the same moment. I couldn't change it because it wouldn't be the same moment if I changed it. If I dropped myself back, I would have exactly the same experience. I would not know that I've gone and recorded the last 10 minutes of this video. I would not know how I said it or anything like that. I would just say, I'm here now, and I was there then, and I will be there in a moment. And then in the next moment, I'll say, here I am in the next moment. And I was in that previous moment. And then the next moment, I'll say, I'm in that next moment, and I was in the previous moment. And so that's how you sort of have both at the same time. You're experiencing from every time within your life, but from within each moment, it just feels like I'm just in the moment. That's just our nature as beings in time. And so we can represent it in a couple of ways. I've already tried to do this, but both of these ways, or all of these ways we could represent it, I think, are deficient to the extent that they implicitly place time within time. So I've already been talking about it in terms of dropping myself back into a moment 10 minutes ago. But you see that is already implying that there's this time that's beyond time, right? That there's a dimension of time which I can move in, which isn't just the time of my life, and which I can then sort of drop my perspective back, and forward and move it around. But actually that dimension doesn't exist. There's only the dimension of time which the events of my life belong to. So just understand that when we're using these metaphors, they are metaphors and they're meant to point to something beyond them. And that something beyond them is kind of hard to state, because when we try and picture something and we try to imagine something, we automatically bring time with us, because time is fundamental. It's something that comes with us into every experience. And so we just have to work with that. But there's two ways that I've put here that we can think about this. So we could picture ourselves as forever living every moment of our lives simultaneously. So I'm always experiencing myself now, when I was 10, and when I will be 70. And in each of these moments, I feel this moment is the present, and I was just in the moment before. That's what I was just talking about. So we could say that we're always living every moment of our life. We're always living every moment of our life. And from each of those moments, from the perspective of each of those moments, then it feels like we're moving forward in time. It feels like we're only here now, and we're no longer where we were a moment ago. And it necessarily feels that way, but it's not that way. Now, of course, to say we're forever living every moment of our lives is, again, invoking that other dimension of time. And so that's what reveals this as being a metaphor. Again, the best way to say it that I can think of is just to say that every moment in our lives exists, that no moment doesn't exist just because it's past or present in relation to our current perspective. We can also picture it as a cycle, like the eternal return. We could say I subjectively live my life all the way through, and then I return to the beginning and live it through again. And so we could just say that we do that indefinitely. Again, it's picturing it as being as time being within time. There's the time of my perspective, and then there's the time of my life. But that's not the case. There's only the time of my actual life. The point is, though, and this is what both of these and all of these metaphors point to, all of my life exists, and all of it is a life, animated, experienced, lived. I can't emphasize that last sentence enough, so maybe actually I'll just say it again. The point is that all of my life exists, and all of it is a life, animated, experienced, lived. So if we were talking about something that didn't have experience, I was going to say a tree, but I'll be even more, I want to rule out any possibility of consciousness, so I might say a stone or something like that. Panpsychists in the audience, just bear with me, forgive me for this, but let's say a stone. So a stone, we can say that it exists in the past, it exists in our present and our future. It exists when it was created, it exists when it will eventually break down, or when the earth will be swallowed by the sun, or whatever it may be. But we wouldn't say it's like experiencing it. It's got its own subjective perspective. But for a human being, that's definitely the case. And that's because we're alive. We are animated, we're experiencing beings, and we live. And so any instance of me at any point in time, maybe instance is the wrong word, any location in time, which is part of me, which I'm at, is also lived. So if I'm an experiencing being, I'm experiencing myself when I'm 70, and I'm experiencing myself, or I'm experiencing when I'm 10, and I'm experiencing to the extent that I can experience, which is not negligible, when I'm 10 months old. And in all of these times, I'm experiencing my life, which exists as an object in four-dimensional space-time, is animated. It's alive. All of it is alive. Not just this one particular moment that we single out and say, this is the present. And so this, maybe I'll just mention one more point before talking about free will. This is something that I didn't explicitly include in the article, I think. But because eternalism isn't our everyday way of thinking about time, it's easy to slip into misleading language. So I've sort of already talked about the difficulties that we have in picturing it and talking about it, using language about it. One of the ways that we can do this is you might hear the view of eternalism expressed as saying that everything exists simultaneously. Everything exists all at once. Everything exists simultaneously. And that can be helpful to kind of get you to grasp what's being said, what's being expressed, but should not be taken literally. All eternalism says is that everything in space-time exists. Each event exists at its own location in space-time, even if this doesn't coincide with an observer's particular now. And so it's not that everything exists simultaneously. Again, it's just that everything exists. Everything exists. Everything has its own moment, its own location in time, just as it has its own location in space, but it all exists. So I thought that would be helpful to clarify at this point. And then the last major objection, which is a major one for sure, is that it seems to imply that we have no free will, that we're thrown into our already made lives and fated to live them out. So if I go back to my example, if I throw myself into my perspective, if you will, into 10 minutes ago, then I have to live out the 10 minutes that have preceded now. I have to live them out exactly as they actually happened. I'm determined, right? And so you could also say you're sort of like thrown into your life, and your life is already determined. It's already, because it already exists. The future of a baby completely exists. Just not now, but it completely exists. And so the poor baby is fated to live out a particular life, and so it has no free will. But I would say that's not the case. So firstly, because eternalism doesn't require causal determinism, it just says that whatever happens exists, regardless of how it comes about. Human free will is just as compatible with eternalism as a universe fully determined by physical laws. Secondly, if free will exists, then whatever I do then whatever I do, if free will exists, then whenever I do something, I freely do it. From the perspective of this moment, if I choose something in the future, it's not that I can't do otherwise, it's simply that I don't do otherwise. And if free will doesn't exist, then we're no worse off under Presentism, then we're no worse off under Eternalism than we would be under Presentism, because either way, human free will doesn't exist. So hopefully you can kind of see what I'm saying there in terms of Eternalism just says that whatever exists, exists. Whatever happens, exists. It doesn't say how things happen or why things happen. It doesn't need Nietzsche's supposition of sort of radical determinism, that everything in the universe necessarily flows from the previous state of the universe or something like that, the previous physical state. It doesn't require that at all. It could even be that certain moments are radically, like two subsequent moments are radically discontinuous from each other. That wouldn't break Eternalism. But what Eternalism would say is that first came this moment, and then, well, first comes this moment, then comes that moment. And likewise, you can factor in free will. All that would be saying is that in the future, and so I'm sitting here, I'm recording this video on this particular day, and in the future I'll do something in particular, which might be really good or it might be really bad, but I'll do the thing. And so if free will exists, and I freely do it, right? So that if I'm being as free as I possibly can in that moment, then that's a free action. It's as simple as that. Then that's a free action. The fact that it exists in the future doesn't make it less free if it's my action. And I think there's a kind of confusion that comes in here when we're thinking about this, because just because it happens doesn't mean that it wasn't free. Likewise, we could look at the past and we could say, I did something in the past, either something that I really like or that I really don't like, but I did it. And then we could say, okay, free will exists. We could posit that. We could assume that. And then we could say, okay, in that moment, I was being as free as I possibly could, right? So I wasn't constrained in any obvious way. I wasn't delusional. I was deliberating and I decided to do the action. And then I would say, okay, well, that was a free action. The fact that it's happened, the fact that it is a particular action that exists in the past, doesn't take away from its freedom. That's basically the insight here. And so I would say that the same thing is true in regard to the future. If you're not happy about a possible future action and you feel constrained by that, you can act differently now. Obviously, we don't know what we'll choose, so we can't take that into consideration. It doesn't really affect us, and so it only comes through in this kind of hypothetical scenario. But I would say that the idea that Eternalism rules out free will is just not accurate. So we've seen how modern physics makes a literal interpretation of eternal return untenable, even as it establishes a new conception of time. Nietzsche's idea returns with greater force in eternalist guise, and we'll call this the Eternalist return. And so this is now leading into the third and final video that I'll do, which is talking about how do we live an eternalist life in the best way possible. So this is very similar to Nietzsche's challenge of how would you live your life if you knew that it would eternally recur. Instead of saying our life will eternally recur, we're saying that it already is eternal in that eternalist sense. And so the third video will deal with that. But before I close off this video, there's just a couple of things that I want to note. And the first thing is a passage that really struck me that I read as a teenager in a book by Joey Comeau called Overqualified. And so I'll just read that out. Everything that has happened or will happen exists together, just at different times. People die, but that isn't any different from the edge of a table. The table is still there, it just doesn't stretch that far. And I think this is a really beautiful and profound quote, especially in regard to thinking about death and thinking about people's lives in relation to yours. People don't go out of existence, but people exist. They live and exist in different times in relation to each other, and sometimes those times overlap, just like sometimes spatially we come into contact, and sometimes those times they don't fully overlap. One ends before the other, or they don't overlap at all. We live in vastly different eras or epochs. But that doesn't mean that they don't exist. They do exist. They exist in that time. And because they're living and because they're experiencing, they live and experience in that time. And I think that this is a purer conception than Nietzsche's conception, which requires objective recurrence. Recurrence would only beg the question, well, are the other iterations of me really me? Right? So if the whole universe will recur exactly as it is, and therefore I will recur exactly as I are, nevertheless, is that me? Is that person me? Should I identify with that person fully? That person is distinct from me in a sense. I mean, they come later than me, and the previous iteration came before me. So there's at least an argument you could make that they're not the same person. But an eternalist return escapes this problem entirely. It says, I am exactly who I am, my every contour in space-time. So with an eternalist return, if you will, with eternalism, you are just saying, I am exactly what I am. And that is eternal. So there's no need to multiply selves. You are exactly what you are. And so then I go into what it means for us practically. And actually, there's one more thing I'll mention here just before I go to talk about why I might be radically wrong. And that is, I've said that eternalism isn't our everyday way of thinking about time, but there is a sense in which it is intuitive. Whatever I've done or experienced, it was me doing or experiencing it. It forms a part of who I am. In these ways, it seems I'm not only a point in time, something only existing in a moment. More broadly, it seems once something has happened, it really has happened. It's out there or back there in being. So we also have this intuitive sense of things. We have that intuitive common sense, everyday way of thinking, which is to say that the events in the past no longer exist. They do not exist. But we also have a sense in which they do exist. They really happened. We can't erase the fact that they happened. And I think that depending on our emotional state, sometimes we lean into presentism or lean into eternalism more. So for example, when we lose something we love, we bewail that loss as a presentist, as though it had utterly passed out of existence. But when we're ashamed of something we've done, we bewail its continued being, even if no one else remembers it. And here, we're instinctively eternalist. It bothers us. It upsets us that we did that thing again. Even if no one cares, even if no one remembers, it doesn't matter. What matters is that it happened. If it's serious enough, at least. What matters is that it happened. We can't seem to get rid of its reality. And so here we're a bit more eternalist. So this whole video and this whole essay, essentially, has been talking about why modern physics actually gives us a way to understand the core insight behind Nietzsche's eternal return, and why essentially everything is eternal. And now at the end I have to include a large caveat, which is that physics hasn't reached its final form. So while the theory of relativity does strongly imply eternalism, this does not hold for all of physics, because we also have quantum physics. And the popular Copenhagen interpretation of quantum mechanics does seem to require an absolute present, in which the possible becomes actual. Now, not every interpretation of quantum mechanics requires an absolute present. So for instance, the many worlds interpretation, where every event splits off into the different possibilities that come from a particular event, split off into different universes, doesn't require an absolute present. But where possibility collapses into actuality, and that really happens in a sense, that understanding of quantum mechanics would seem to imply an actual absolute present in which that transformation occurs. Now, relativity and quantum mechanics are the best theories we have for explaining the largest and smallest structures of our universe, respectively. But physicists have struggled for decades to unite them. Assuming a union is possible, we don't know whether this will reduce quantum presentism to relativity's eternalism, or vice versa. So it could go one way, or it could go the other, or it could introduce a third alternative that we haven't thought of yet. Suffice it to say, we haven't heard the last word on time. So while the essential insight of Nietzsche's eternal return is extremely plausible given modern physics, it remains one perspective among others. And both of these facts may well have pleased Nietzsche. That is to say, the vindication of his idea of the eternal return, or at least the core insight behind it, and this kind of perspectivist, relativist situation in modern physics, which we have, which isn't totally resolved. Those would both appeal to Nietzsche in different ways, I think. At the bottom of the article, I've put the Nietzsche stone, which is sort of what I referred to when I was opening the article, which you can hear in the first video. This is the stone, the sort of pyramidal stone that Nietzsche was standing next to when the idea of the eternal return came to him, or came upon him. It was almost like a revelation. And so that's what I've included there. So that is this video, which is the most extensive video and the most important video, because again, it's covering the main thesis of what I'm trying to argue, which is that modern physics vindicates, if you will, or at least strongly supports the idea behind Nietzsche's eternal return. But then, as I've said at the end, it's not finally worked out. I think it's fair to say that relativity is necessary to deal with the large scales of the universe, more or less, and it does seem to imply this eternalist view. So we can at least say that is true. How that works with quantum physics ultimately, we don't know, but we at least have one plausible way of understanding it. And again, I think there's other philosophical problems with presentism, which partly McTaggart outlines, right? The circularity and infinite regress implied by it, if you're considering a B series and an A series. And also there's other views of time, but I think that they don't really get beyond this either. So, for instance, another major view of time is the growing block theory, which is to say that the past exists, the present exists, and the future does not yet exist. First of all, we've seen that doesn't really work with relativity, because it seems that there's no possible future that could just be purely future for every possible observer. And so, but also it's a kind of combination of the two views in a way. So I didn't want to explicitly introduce it into here. It seems to me that eternalism is the most plausible idea, and so perhaps we should live in light of it.